Okay, in this lesson we're looking at force and velocity as a vector. So what's the goal for this particular lesson? I can apply previous understanding of vector addition and subtraction. So we're going to have to be able to use our addition and subtraction we just finished, and we're going to start applying them to real-world situations involving physics. Now, before everyone panics, we're more looking at the vector situation, and we're going to show you the examples that are tied when I talk about physics. So no one panic too much yet who hasn't taken the physics. So, force. We're going to just quickly talk about Newton's 3 laws here. And no, you don't have to memorize them. No, you don't have to regurgitate them. I won't ask about them on the test. Newton's first law, an object will remain in its current state of motion until acted upon by an unbalanced force. What does that mean? It means that if you have your computer in front of you right now, if it's not moving, it's never going to move until you give it a push. But don't do that. All right? You don't want to push it off the desk. If something is rolling, something's not going to stop rolling until it hits a wall or whether you jump in front of it. So Newton's third law, or first law, simply means that. Newton's second law is just the formula F equals mass times acceleration. This is the one you want to put on your cheat sheet, and I'll talk about the why and where. Where when we're talking about gravity, for example, I'm using 10 meters per second squared down. Acceleration, or acceleration due to gravity is a vector, and we're going to use 10 for this course. And finally, every action has an equal and opposite reaction. So you can think of it in terms of a fight. Go to the principal's office. The principal asks, why were you punching this student in the face? The argument is, no. The student was headbutting my fist. It wasn't my fault because look at my fist. It experienced the same amount of damage as the face. Every time you push against something, a wall, for example, it pushes back with the same amount of force. So keep that in mind. So we're really only looking at number 2 there when we go through to do the questions. So here are the examples. I'm going to do this example twice. I'm going to do it once geometrically and once algebraically. So a 5 kilogram sign is suspended as shown. Determine the tension in each wire. So geometrically, start off with a vector diagram. So what forces or what vectors are applying to this object? So the box itself I'm going to represent as the dot. And it's going to have a force pulling down. So this is force due to gravity. So the people that haven't taken the physics, force due to gravity is going to be mass times acceleration, which is in this case 5 kilograms times 10. So the size or magnitude of this vector is 50 newtons, and it is down. The other 2 forces come from the tension in these wires. Okay, the tensions in these wires. So we're going to have a tension. I'm going to call this one tension 1, and this one tension 2. All right. Now, when nothing is moving, the resulting vector is the 0 vector. So because this square, this box isn't falling, it means that the forces are balanced. It means the sum of the forces are 0. So that means that the resulting vector is 0. So what does that mean geometrically? That means geometrically, we are going to have a closed triangle. To have a zero vector, that means you have to end up, your end point has to end where your start point is. So that means that for the diagram, so this is the diagram that we're going to use here. That means that I have a force pointing down. That's the 50 newtons. The vector, the tension vector, goes in this direction. And then the second tension has to end up at the start point to have a vector of 0. So there is my 0 vector, the dot. So it must be closed. So geometrically, triangle, and I'll put in brackets any shape, doesn't matter how many vectors. We have 3 vectors, so it's going to be a triangle. Triangle must be closed when the resultant equals the 0 vector. All right, so there we go. So we know what the value of the force is. Now let's see if we can figure out some angles here. So looking at the original diagram, tension 1, okay, this one right here, we know from good old grade 9 geometry that if I draw, that's not going to be very nice there because it covers everything up, but we get what we call the Z pattern. The Z pattern right here, which means that the angle between tension 1 and the horizontal is also 60 degrees. So if I come back here to my diagram that I just drew, that means that that angle is 60 degrees, which means that because the force vector is vertical, we have a 90-degree angle in there in total. So that means the angle in here has to be 30 degrees. All right. Similarly, if I draw the Z pattern the other direction, oops, and I missed completely. I wanted to go down here. We get a 45-degree angle, and from the Z pattern, that's going to be 45. So that means that with the horizontal, we have a 45-degree angle, which means this internal angle will be 45 degrees. And when you know 2 angles, you know all 3 angles. So the 45 and 30, that's 75. So that means that this angle here is 105 degrees. So that means that we can use sine law, and we know all our angles and one side. So to finish the question up then, to find the unknown T1 and T2, I'm just going to do magnitudes. I'm going to use sine law. So sine A over A equals sine B over B equals sine C over C. So that means I'm going to use my force vector. So that's going to be sine of 105 over 50 equals sine of 45. And remember, we're dealing with just magnitudes in this direction, in this situation. So magnitude of T1 and sine 30 degrees over the magnitude of the second tension. Breaking that apart, because it's a proportion, we end up with sine 105 over 50 equals sine 45 over the magnitude of the tension, or T1. Rearranging that, we find that the first tension is going to equal 50 sine 45 over sine 105. That's measured in newtons. So we've solved for the first tension, just like that. The second one, sine 105 over 50 equals sine 30 this time over the second tension. So that means my second tension, rearranging, is going to be 50 sine 30 over sine 105, again in newtons, and there we go. So in this case, for this particular question, I would actually use the geometric method. That would be my preference of choice. Therefore, magnitude T1 and magnitude T2 as shown above. So I'm going to do the algebraic one side by side so you can see the comparison. Some people are going to stick with the algebraic method all the way through, and that's perfectly fine. It's not going to make a huge difference when you compare the two. So what I'll do that in the next video, just to make sure I have enough time.